this is a recording for math analysis, and this is 2.4 examples, and we are finding zeros of polynomial functions. And so I left you with asking you to find P over Q and to kind of find these upper and lower bounds. So I'm going to show kind of my graph that I came up with and my window. It's a little hard to see because the cursor on the graphing calculator was kind of in the way, but let me just kind of let you know this is -3 right here to 7. So if I kind of write that on here, that's -3, this is +7. And I know it's, you know, I want to kind of think of all the things that I can do. So this is a positive x to the even power. So I knew right away that in the end, it's going to go, you know, to positive infinity. And maybe I could have shown more of it there, but it's going to go up that way. It's going to go up that way. Yeah, really, because how am I sure that that's going to happen? But I think that's where the boundary is. And then really this, you know, looks like it might be 1 or 2, but this is -250. And this is +250, and it's going by 50s as we look at that. So it looks like -3 is a lower bound. Lower bound, we're going to say, is -3, and an upper bound is 7. And, you know, maybe even when you were looking at a table of values, if you did, you even notice that that for this problem, excuse me, that for this problem, maybe some of the zeros are, you know, integer values that are right on there. And then we're going to look at our P over Q. So for this one, you know, we've got 12 here, but we've got 1 there. So P over Q is just all going to be over plus or minus 1. So they're all going to be whole numbers. But 12 has a lot of factors. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12 are all of the things that I could try as I go. And, you know, so we've got a lower bound of -3 and an upper bound of 7. So we're not going to go, you know, above or below. And it asks us to explain our reasoning using this upper and lower bound test. So I'm going to take -3, and really, you know, suppose I had said that I thought -4 was the boundary. That's okay too. You know, it would certainly be. But let's do that synthetic division with -3 and see what happens. So 4, 3, 2, 1, 0. So we have 1, -4, -11, -4, and -12. And so when I do that, let's see what happens. I get, bring down the 1, -3, so that's -7. This is 21, so that's 10. This is -30, so this is -34. This is 9, 10, 102. And so then that is 90. So look at what's happening. So this is positive, negative, positive, negative, and positive. So since these are alternating, and you know, even if one had been 0, these alternate, non-positive, non-negative, and so that is the lower bound. So -3 is lower bound. And you know, I even said to myself, oh, I could have gone further that way. But by trying number 3 and doing that synthetic division, I can see that, yes, it is not going to crinkle back down and up at some point in time. That is as low as we need to look because last line in synthetic division is alternating. oops, sorry, non-positive, non-negative, non-positive, and non-negative. So that's the lower bound. Let's check that 7 is the upper bound. And, it kind of looks like it's going steeper there. So, maybe that's not too far-fetched in our minds. But we'll still show that as we go. So let's do 7, 1, -4, -11, -4, -12. And so for this one, we bring down the 1. This will be 7, 3, 21, positive 10 this time, and 70, so 66, and that's 2, 4, 462, and then, in a way, I don't even have to find that because I can just tell it's going to be positive. So these are, for this way, positive, 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 or just non-negative, positive, positive. So think about that too. If those are all positive, if I tried something like 12, those are going to be even bigger numbers, so it's not going to happen that way. So 7 is the upper bound because the last line in synthetic division, is non-negative, we'll just say. So now what that did for us is it eliminated our need to use like this 12. And not only that, because we were using a graphing calculator, as we kind of think about that, we could say at this point, and maybe even looking at our table of values, it looks like maybe it hits there at -2, and maybe it hits there at 6. So those aren't for sure, but we can surely validate that using synthetic division. And so this time I'm going to use the short version of synthetic division. So 1, -4, -11, -4, -12. And I'll try, it doesn't matter which one I try first. I don't know, for some reason I'm going to try 6. So I bring down my 1, 6 minus 4 is 2, 12 minus 11 is 1, 6 minus 4 is 2, and 12 minus 12 is 0. So this works, yes. And then I can just use this new row here, and I'm going to ignore that, and I'm just going to do these. Sometimes I cross those out, otherwise I tend to look at them. So -2, bring down the 1. -2 plus 2 is 0. This is 0 plus 1 is 1. -2 plus 2 is 0. So that one works. Yes, that's a 0. And then what would this part be? X squared plus 0x plus 1. So that's x squared plus 1. And, think about setting that factor. That's a factor. Setting that factor equal to 0, we get x squared equals -1. So that is a non-real value as we go. And so we found the upper and lower bound, and we can say that our zeros, the zeros were 6 and -2. So we also found that as we went through that one. So now we're going to look at even another way to refine this, because it could be that we're in a situation where we have to do a lot of synthetic division. And so it's nice to maybe have other things that might help us narrow that down. And the next one is Descartes' rule of signs. And so, I did that. And so here is Descartes' rule of signs. Descartes' rule of signs says this, that, the same thing, if this all happens, then the number of positive real zeros is equal to the number of variations in sign of f of x, or less than that by some even number, and the number of negative real zeros is the same number of variations of sign of f of negative x, or less than that by some even number. So pause this and write a good note about Descartes' rule of signs, because it is important to us, and then we'll apply that to a problem or two. So moving on, let's look at a problem. And this one is just asking us to describe the possible real zeros. So we're going to just use Descartes' rule of signs to do that, just to kind of get an idea, of what's happening there. And, there we go. And we're not going to actually find the zeros in this one. We'll just kind of say how many we think there are, positive and negative. So number 5, f of x is x to the 4th minus 3x to the 3rd minus 5x squared plus 2x plus 7. And so what we're going to do is we're going to look at the sign changes there. So this one's positive, this one's negative, so there's a sign change there. This stays negative, this goes from negative to positive, so there's a sign change there. This one stays positive. So that means that there could be 2 positive real zeros, but then we can go down by 2, and so there could be 2 or 0. So we'll say 2 sign changes for f of x. So the number of possible real zeros, and kind of notice it is real, so it's not just saying rational, they could be radicals and things like that, is 2 or 0. So if we find one, we know that there's another one, real at least, or there might not be any at all. So then the second thing we have to do is look at f of negative x. F of negative x, which means that we put negative x in each place of x. And we do want to put it in parentheses. So negative x to the 4th minus 3 times negative x to the 3rd minus 5 times negative x squared plus 2 times negative x plus 7. Let me just tell you, as a student of mathematics, that people often make mistakes if they don't write that out like that and then figure out what it is. So just be cautious with yourself. Know if you're prone to errors, and the more work you show, the better. So negative to the 4th is a positive, so this will be x to the 4th. Negative x to the 3rd is a negative, but then we multiply by negative 3, so that will be plus 3x to the 3rd. So essentially, if it's even, it stays whatever sign it was. If it's odd power, then it's going to change to the opposite. So again, this one becomes a positive, but it stays the same. This one is a negative, so it'll be minus 2x and then plus 7. So that's our rule. Now let's look at our sign changes. So this one's positive, positive, and then goes to negative. So there's a sign change. Negative to negative stays the same, and then negative to positive, so there's another sign change. So there are also 2 sign changes for negative f of x, or f of negative x, excuse me. So the number of possible possible real zeros. I just am reading up there. Number of possible, I wrote, and then I should have written positive. my apologies, the number of negative, I'll fix that, real zeros is also 2 or 0. And so go up here and maybe I'll write it in a different color here. Maybe just a different, this should have been positive instead of possible. Boy, sorry about that. And so then when we're doing synthetic division, and ideally, sometimes, maybe there's no sign changes in one or the other, and then there might be no negative or no positives, so we don't even have to try any. And maybe there's one, and so if there's going to be like one negative, I would start trying negative numbers. If there's like one positive, I would try finding positive ones as we go. So let's move on to the second part of this lesson, and that is looking at complex zeros. So now we're going to know our zeros and then find a possible polynomial function. So this will be fun. Let's move along, and here we go. So when we use Descartes' rule of sign, the number of real zeros includes repeated zeros. Therefore, a zero of multiplicity m would be counted as m zeros. Just a little note to self. Just like quadratic functions can have real or imaginary zeros, polynomials of higher degree can also have zeros that are complex. And so this is the fundamental theorem of algebra, and it allows us to kind of think about how many zeros there are. So a polynomial function of degree n, where n is greater than 0, has at least one zero, real or imaginary, in the complex number system. The corollary to that is if it is a polynomial function of degree n, it has exactly n zeros, including repeated zeros, in the complex number system. So we can kind of find all of them there. And I'm going to just slide this up so that I can kind of see the linear factorization theorem. And that states that if f of x is a polynomial function of degree n greater than 0, then f has exactly n linear factors. And so you can maybe jot that down to kind of get a sense of what that is, where a sub n is a non-zero real number, and then these c1, 2 to cn are the complex zeros, including repeated zeros of f. So I'll pause this to write down the fundamental theorem of algebra and the linear factorization theorem, and then we'll look at conjugates. Okay, moving along, then there's a conjugate root theorem, and that is if a polynomial equation has a root of the form a plus bi, then its complex conjugate a minus bi is also a root. And you can use this theorem to write polynomial functions given its complex roots. So not only that, if we're told one complex root, we're automatically going to know a second one as well. Again, pause this if you need to, and then we'll move on. Now, moving on, this is number 6, and the directions are write a polynomial function and it says of least degree. I'm not going to write that down, but you can. With real coefficients in standard form that has -1, 2, and 2 minus I as zeros. With zeros, I'll put a colon there, maybe -1, 2, and 2 minus I. So a hint to ourselves is when they say 2 minus I, then always the conjugate will be another 0. We're not told, but 2 plus I also has to be a 0. Also has to be a 0. So that's kind of the extra one that we get. So think about this is probably going to be a 4th degree equation. So also, I'm just going to remind you that that means that x equals -1 is a 0. So if we kind of add 1 to both sides, x plus 1 equals 0. That's the factor. X equals 2, so we'll subtract 2 on both sides. So x minus 2 equals 0, so x minus 2 is a factor. And, you know, the real way that we kind of do that, I'm going to maybe get rid of that. The real way that we do that is we say if the root or 0 is c, then the factor is x minus c. And that's why it is, but just to let you know. So the complex ones are a little tricky to write, so just be cautious. So we're going to have x minus -1. We're going to have x minus 2. We're going to have x minus, but then I'm going to put that complex number in parentheses, 2 minus I. And then we're going to have x minus that purple one. And we'll put that in its own parentheses, 2 plus I. A hint I'll give you is, you know, kind of work with those two. And if you want to work with these two and kind of get that and then get this and then just multiply those two answers, that's fine. I wouldn't start multiplying like these two or any of the complex one with a real one, because when you multiply these complex conjugates, the imaginary part is going to drop out and you're going to get a real answer. So that's kind of going to be a good thing. So I'm just going to make that back into a plus. And the way that I'm going to do that is I'm going to multiply those two and I'm going to multiply those two. That's going to take me a little bit. So let's distribute that out. X times x is x squared minus 2x plus 1x or plus x, and then minus 2. And oh, I'm not even ready to multiply that one. I want to distribute that first. So it's okay that I multiplied these. So I'm going to distribute now that negative there and this negative there. Notice there's still going to be kind of conjugate-y looking, x minus 2 plus I and x minus 2 minus I. But you know, the signs are kind of different there. Well, I had already started this first one, so I'll keep going. So x squared minus x minus 2 is that. Now, on this second one, now this is going to be kind of this long thing. I'm going to take x times each of those to get the first term. So I'm going to get x squared minus 2x minus ix. And then I'm going to take -2 times each of these. And that's going to give me minus 2x and plus 4 and plus 2I. And then I'm going to take I times each of these. And I'm going to get plus ix. And then minus 2I, and then minus I squared. Note to self, we just said that the i's should drop out. So x squared minus x minus 2 is the first one here. And then let's see what happens here. Let's just look for things that are going to cancel. I've got minus ix and I've got plus ix. I have plus 2I and minus 2I. So those all cancel out. Remember, I squared is -1, so I have minus -1, so that's going to be plus 1. I'll just kind of scratch that out and write it in so that I can kind of figure things out. So I've got x squared and minus 4x, it looks like. And then I've got the plus 4 and the plus 1, so plus 5. Now I'm going to do that exact same thing. I have two trinomials, three-termed things, and I'm gonna just kind of distribute things out. So I'm going to take x squared times all of those, and that's going to give me x to the 4th minus 4x to the third plus 5x squared. Then I'm going to multiply each of these times, or x. Oh, I don't like that color. It's kind of too close to, I'll just use red. I'm going to take x times each of those, or negative x, so that'll be minus x to the third plus 4x squared minus 5x. And then lastly, we'll multiply that, oops, not that, the negative 2 times each term there, and we'll get minus 2x squared plus 4, or just kidding, plus 8x, and minus 10. And then we'll just combine up all of our like terms, and we get x to the fourth. That's the only fourth one. And then minus 4x to the third minus 1x to the third is minus 5x to the third. 5x squared, 4x squared, 9, minus 2 is 7, so plus 7x squared. And then the x is minus 5. And I think I had a mistake maybe here or not. And so then that is, oh no, I'll have plus 3x and then minus 10. And so there, this is the function, and maybe I'll put on there that that was f of x. Could be this. And you know, like, think about the fact that we could have, let me get rid of all that there, f of x equals, we could have like multiplied everything by 5 and just gotten something different there. So if for that function rule, we know that these are the factors, and 1, 2, 3, 4, there's the 4 zeros for that as we go. And so that is writing a polynomial function, knowing the zeros as we go. And I think we will call this the end of this part. And there's a lot to digest in this. Maybe you can kind of be starting on the homework, and we'll look at what it means to be irreducible over the reals if we just want to use real numbers in the next part of still 2-4. So this concludes this part.